Okay, so section 2.1 is second order linear differential equations. So in chapter 1, we talked a lot about first order linear differential equations. So again, now we're just going to be talking about second order. And remember, the order is the highest derivative of our differential equation, and so our highest derivative was 1, but it could be higher than 1. Definitely could be higher than 1. So our second order, right, that's before in chapter 1, right, it was 1, right, but now in chapter 2 and so forth, right, it could be greater than 1, right, so it could be 2, 3, 4, 5, 6, and so forth. So here's our second order, and we've already talked about what linear means in differential equations. So in this section, again, we're going to be solving these differential equations and finding their solutions, their functions, but specifically with order greater than or equal to 2. So second derivative, third derivative, fourth derivative, and so forth. Okay, so a linear second order differential equation can be written in this following form. So we have a of x, y double prime plus b of x, y prime plus c of x times y equals, right, some function of x. And remember, these are our denotes, our primes denote derivatives, so order 2, right, here's the first derivative, and our y, remember, is our solution to our differential equation. Okay, so this is the general form of a second order linear differential equation. Okay, so one thing, there's a lot of really cool things about this equation. One of the things I want you to see is that this should remind you of something in algebra. And think of these guys as coefficients, right? Let's say I want to let a of x, right? Let's just say I call that a. Y double prime plus, and then again, let's just call that b, y prime plus maybe just little c, y equals f of x. This guy should, if, right, this is the second order, you could think it's a power of 2. It's not the actual power of 2, but this should remind you of, oops, maybe, ax squared plus bx plus c, right? This is a, whoops, this is a quadratic expression, right? That's not a prime. This is a quadratic, I mean specifically polynomial. And when you work with quadratics in algebra, usually you factored the quadratic equations, right? And you determine the roots of the polynomial, or sometimes called the zeros. In this case, they're going to be our roots and are going to help us construct our solution to our differential equation. So this is the key to this section, is really knowing how to factor this type of polynomial. Okay, so big picture here. So this is very important. I want you to note this f of x, okay? When f of x is equal to 0, then we say, right, let's maybe call this, oh, I don't know, equation 1, okay? Then we say equation 1 is a homogeneous, right, or homogeneous, of course, second, right, order linear differential equation. Okay, so when we're working with second order differential equations and it's homogeneous, we know that the right-hand side is 0. If it's not 0, then it's just non-homogeneous. Now there's a big difference between, let me just go ahead and write that down. There's a big difference when we talk about first order linear homogeneous, right? Differential equations, of course. And then now we're talking about second order linear homogeneous differential equations. Well, let me just go ahead and write it out because I do want to underline something. So homogeneous. Okay, these these terms actually mean something completely different when we're talking about the order of the differential equation. So one of the concept questions asks you to explain this. What does homogeneous mean when we're talking about when we're given a first order linear differential equation, and what does homogeneous mean when we have a second order linear differential equation? Well, I just gave you the second part, right? We know when a certain form is equal to 0, but it doesn't mean the same thing here. So that'll be a concept question that I'll let you think about. Okay. And let's see, some other good points that I wanted to make sure to emphasize. Okay, so this guy here, our star equation. So I used x, but I'll go ahead and, well, let's just go ahead and write x. It doesn't really matter. Okay, this here is, we know that this is a quadratic equation. Right here, it's just, it's some polynomial, but it doesn't actually have an equal sign here, so it's not an equation. But this is a quadratic equation. Again, this looks very, very similar to our differential equation up here, right? Of course, with a 0. So we're gonna again use what we know to solve this differential equation. And this quadratic equation, the book actually calls it the characteristic equation. So again, you can call this, this is a quadratic equation, but they also call this, the whole thing, they call it the characteristic equation. Okay, so this is the key to solving the second order linear homogeneous, right? It's got to be equal to 0 differential equations. And this is really cool because we know how to find the roots of, in algebra, if you're given this equation, right, and x is some unknown number, right, not a function, we can find the roots by, either, factoring. If it's not factorable, maybe using the quadratic formula, which you had a homework problem in chapter 1. There's a lot of types of factoring. We've been talking about factoring out a GCF, a greatest common factor, that was on your test. With the partial fraction decomposition, there's a reason why I put that problem on there. We have a squared minus b squared, right? The difference of two squares. So you want to use your factoring techniques. It says factoring techniques. Okay, in this section to help you find the general solution of these differential equations. Okay, so I'll stop here because it's getting close to 10 minutes, and then I'll go ahead and do some examples, and hopefully that will help kind of cement this idea. Again, key words here: quadratic equation, characteristic equation, degree is 2. And okay, so I think that's it. I will continue the fun in the next video.